Okay, so let's get started. Today we'll try to solve this diagonal traverse problem, which is basically, so brief overview would be, let me see, do I have a pointer? Yeah. So brief overview would be we have m by n grid, and how can we traverse it, all the diagonals. And if you notice, let's just see one of the input statements first, like example, and then try to work our way backwards. We have this, a 3 by 3 matrix, and for that we will have the traversal as this way: 1, 2, 4, then up for 7, 5, 3, then 6, 8, and 9. And the main intuition I have from this puzzling piece is uh, we will have two ways motion going upwards and downwards, so we have to accommodate that, and as well as thinking about like how many diagonals I'll have. So when I when I solved this problem for the first time, my intuition was try to figure out how many diagonals we have. For this m by n, we have 1, 2, 3, 4, 5, because it's just basically 3 plus 3 minus 1. And my kind of visualization for that would be, suppose if we have a grid like this, okay? So let me just rather draw it, okay? So if we have a grid like this, okay? Uh, right. So we have 1, 2, 3 columns plus 1, 2, 3, 4 rows, and this is the formula. And my intuition for that formula was noticing this part, like divide this piece into two triangles, this one, so we have one triangle here and one triangle over here. So when I noticed it for the first time, my instinct was one diagonal, two diagonal, and this is the third diagonal for this triangle. And similarly, this one has three. 1, 2, 3. And since the middle one overlaps, I will just take -1. And that idea really holds, because if I kind of draw the diagonal here, we will have 1, 2, 4, this one, this one, this one, and this one. So we have 1, 2, 3, 4, 5, 6. So I think it makes sense for this part. And once I know how many diagonals we have, we can then try to do it. So the way I initially solved this problem was formulate everything, like make up an inequality. I don't know whether I'd have that solution. No, not here. No, no. Uh, it's been a while, so uh, let's see. Okay, I think I can quickly go through that as well. Like the initial solution. Okay, 4 minutes. Since I've already solved it, so it shouldn't take that long. Let's figure it out. We have, firstly, I would take the pieces I and it's equal to left out size, which is the number of rows. Also, n is equal to net 0 dot size, which is the number of columns. Once I have these two pieces, next what I can do is go through the things, like go through what I have. That was my basic instinct. So I have, uh, for r, for rows, it has to be greater than equal to 0, right? and it has to be less than m, right? Hmm. And for columns, it has to be greater than or equal to 0, and columns should be less than n. And after that, so my feeling was, how can I derive an inequality such that I formulate the inequality for only row or column? And the intuition behind that piece was figuring it out, like how the cells are arranged. For example, if I just go through this piece, it would make things a bit more clear. Let's use not red, orange here. So we have not the not this, not this. But then so 0, 0, 0, 1, 0, 2. Then subsequently we go downwards and see is what the cells 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, 3, 0, 3, 1, 3, 2. If you notice, these all the same diagonal, they sum to a specific number. So here we have 1 and 1, 2 and 0, 0 and 2. And these also match, as well as like rest of the diagonals as well. So it was apparently clear to me that R plus C is equal to a specific diagonal, and now my whole job was to formulate or use this piece uh, to kind of get an inequality for either for R or for C, doesn't matter. So basically what I would have a for loop, since I know how many diagonals we have, so we can use this piece, and that we will do for, we will go through it for all the diagonals, and I want to iterate through R here, so that I can grab the rows. And once I grab the row, I will automatically have the column because it's for a specific D, right? Our C is gonna be D minus R, as you have just seen. D minus, so that should be, so that was my intuition behind the problem. Let's see if we can quickly go through it. But I wanted to try a different approach today. Let's see. Uh, we have this piece. What else can we derive? So okay, let's try to work it out this way. We have C, which is, oopsies, greater than or equal to 0 and less than n. Or we will have C is D minus R less than n. And if we calculate it, what we would get is 0 is less than 0 is less than equal to D minus R, or R is less than equal to D, right? R plus R, yeah, less than equal to D, that's one piece. Or we would get D minus R is less than N, or minus R is less than N plus, sorry, N minus D, right? Or, and since we are negating it, right? So that would flip the inequalities, right? Let's see. minus 3 is less than 0. Minus 3 is again less than 1. If I flip it, then it would be 3 minus 1. So, folded then. Yeah, so 7 should be flipped. Is greater than D minus N. So let's keep building on it. Mm, so we have our on the upper bound, we'll have R is less than N, R is greater than equal to C, right? With the lower bound. And if I am trying, for example, I'll have one set. Okay, I'm trying to fit in both qualities. So let's have that. For the upper bound, I want to take the minimum. For the lower bound, take the maximum. So our formula is going to be lower bound should be upper bound should be minimum of V and M. Our lower bound is maximum of 0 and D minus N. Let's see if this theory holds. We will have this as a test set. Doesn't matter what we're talking about. Here D is equal to 2. And that was 2. Our rule is going to start from minimum of D, 2 and M. 2 and M is 3. What's the minimum of 2 and M? It's 2. And it's gonna end at, so our lower bound, upper boundary is gonna be our lower, our upper is gonna be, sorry, my bad. This is our upper, that's our lower. That's gonna be what? 0 and D minus N, which is 0. 0, 0, D minus N is 2 minus 2 minus N is 3 minus 1. So maximum of this D minus N, which is minus 1 and 0, sorry, minus 1 and 0, the maximum is 0. Mm, right? Yeah. So yeah, we will iterate from 0, 1, into these cells, grab the subsequent columns, and get the values. See, this is what I did. And I don't think we have to do it. That's one of the reasons of doing this problem today. But let's quickly. How are we doing on time? Other 15. So let's say our upper is 2, right? Mm, what should is equal to 0? D is less than b plus minus 1, b plus plus. Once we have that, what we can do is for identity r is equal to 0, r is less than, oh no, for each diagonal, we will try to find upper and lower for this specific scenario, right? Yeah, upper is gonna be minimum of t and n, and lower is gonna be maximum of 0 and yes. Now, since I have that, I'm gonna do start R 0, R is R from upper, right? Start R from upper and lower, and start from, if there's no prominent F, Y is greater than equal to 0, and R minus 2 is, we will do RBT C is gonna be D minus, and we'll just get the vector. So let's say we will have this piece, and we vector for the results. So vector of here, and we do push back. We will do matrix of R. So once I do that, I would want to check if our is the of 2 is equal to 0. The reason I'm checking is if it's an so by our logic, I wasted quite a bit of time here. By our logic, our traversal covers this diagonal from top to bottom. So that's fine for odd cells, but for even cells we have to go up. So for that, it's we'll just reverse the diagonal, and at the end we can just push into the result. So let's say we have a vector of integers for result, right? So we would do result dot push back. Oh no, it's a diagonal. We can't push back diagonal into a diagonal. Like vector of integer into vector. So okay. So we will do result dot insert. We do diagonal result.in. Where are we inserting? So insert at the end of the result. Initially it's going to be empty. Then we would, what would we insert? Diagonal top again. Then, then, and once I have these, we would just return result. So, and let's say what? We printed. Wait, M is not legal though. It has to be M minus one, right? And this has to be minus M, so it's gonna be plus one minus two. Okay. Should be. Okay, overflow. So we're doing well. Hmm. For diagonal two, we would have, so we have two here, so we would have minimum of minimum d, which is 2, and n minus 2 is 2. Okay. Lower is kind of maximum of 0 and d plus 1. That's 2 plus 1 is 3 minus n. 3 minus n. 3 minus 3, which is 0. And that is going to be, that's fine as well. So if I have this and this, 2 and 0, start with upper, get the C, column number, we just do diagonal the pushback, specific one, keep doing it as we can, and we should end up with the result. If not, okay, let's see. This one looks fine, but we will try to get it. Breakpoint, 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 and the insertion to resolve this part will be fine. Let's start. We would get this value fine. Our C is A. Our C is 0. Upper is 2. Upper lower isn't changing. Is R and C changing? That would be a good question. See if a few minutes. Yep. So where were we? We were trying to debug this. Let's try. Um, why isn't our C's value changing? Why is it not even popping up? Zero. That's weird. Mm, mhm. C is zero. R is zero. Auto is zero. Let's check our operating model. Oh, that's right, that's right, that's right. It should be zero initially. Mm, so comes zero, one zero zero, then zero. We would reverse it and then results. Right? Yeah. And result changes, right? Yep. And uh, if the x is still zero, right? Oh yes, it should be, yep, zero one that executed. There's a 4 2. That's right, is 4, right? Mm, 4 2 actually 4. So, keep it here. Mm, so it's a find 735. It should become 1 2 4 4 3. 15. There's wrong. We have this piece. Look at the timing from upper very slow to mm, so You will only reverse if it's not zero is equal to zero. Zero mod 2 is equal to zero. Okay, reverse it. Reverse. Oh, by default it's down. Reverse it. It's the default flow. Our R becomes if it's one, then it becomes minimum of one and two. So if you have, yeah, that's also fine. If you have zero and three, two, say three plus one. Yeah, sorry, yeah, but one is the so one. This becomes one, and new row becomes zero. One plus one, two. Minus three is minus one, so it becomes zero. That's also fine. It's working fine. But this, for each diagonal, we have to check such a mistake. Okay, no, we have the diagonal already, right? Yeah. So for diagonal or two is equal to zero, we will just reverse it. Because the way we're going, it's from it's starting from upper, that is 2. So we are going row 2, rows here, we are going up by default. So if it's not, so if it's even, we're going up by default. If it's even, so by default. If it's odd, then reverse it. And yeah, let's see. Okay, yep, should be good. But yeah, see, it's horrible. That was I was trying to fix. So let's try doing it another way. So this time what we would do is basically do a lateral movement. If it's going up, uh, the thing that I brainstormed with GPT was that either we're going up or down, right? And we can just code against these two cases rather than manually figuring out the inequalities. And the way I would do it is basically for each up movement, what we're so for each up movement, we are basically doing, for example, for uh, okay, let's take this. I wanted to get the entrance equal for you. Perfect. Okay, so let's take it to this side. No, let's take it to this side. Go there. So for this, for example, if you're going from this cell to this, we are basically doing uh if you're going up, and we're basically doing r minus minus, right? Yep, that's 0. That's 1, that's 2, 0, 1, and doing r minus minus, and doing column plus plus. And if we're going down, we are doing, for example, from this cell to this cell, we are doing that's r plus plus, and a column minus minus, right? So these are the two lateral movements we're doing. So what I would do is mm, three five times 10 for IGT to 0 is less than what? And how many elements do we have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9. So in times end, right? As if we get 4 times 3 is 12, or 4 by 3. Right? So we will have total n by n times the elements and plus plus, right? So for this, we would either have an up movement or down movement. Let's say our time t initially, what are we doing? We're going up. So volume up is equal to 3. So if up, then we would r minus minus c plus plus, or else r plus plus c minus minus the opposite, right? Yeah. So a few things that we have to take care of is what happens when while going up like this, while going up, I hit the walls. And what are the walls we can hit from while going up? It should be either the top wall, this one, or the what do you call it, the right wall, like either of these two walls. So let's say we have this scenario where we would be doing things like this. So let's say we have this piece, 1, 2, 3, 4. We will have 1, 2, and 3. we have that. And if we hit the top wall, this one, what do we do? So we were going up, up, this is going down, then this will go up, and we did hit the top wall. So for that, we would start, we would do, so, okay. So first thing we would do if r equal to, can do it like this. So it, make this limit at this, and we will try to figure out positions for R and C, right? So let's say we have, so if we don't see this R, and R is equal to 0, R is less than M, or we would, from this loop, we can calculate the C. So our C is going to be D minus, right? Then how do we navigate if a situation, if it's going up? Oh no, we found it somehow else. Let's start from 0, 0. Now, initially, we'll start from 0. Initially, we'll start from r is equal to 0 and t is equal to 0. That's from where we're starting, right? From this cell. So let's keep it that way. Then we would follow the flags as we were, the way we were doing it. So if up, then this. So we will basically handle two different scenarios. I don't know which ones. That should be something like this, and this should be the fallback. And this, let's just put it this one. Similarly, we would have this. So we could also have two cases here where we are hitting what? The left wall or the bottom wall. So for the left and bottom wall, let's say we will have this condition, else another condition, or we would have else, where we would go with r plus plus and c minus minus. So, yep, that's it. Now, since the piece, so we have r is equal to 0, c is equal to 0, we have is equal to true, that's fine. So let's see, let's figure things out. Suppose we have this starting from, if we hit the, when are we hitting the top wall? It's when our r is equal to 0. So let's say we have this, and if r is equal to 0, what do? We just start coming down. So that's one thing. So is equal to false, as well as we do reach this point, our r stays the same at 0. Our column number increases by 1, so C++. So that's one thing. If our C is equal to n minus 1, column minus 1, that is if we hit this cell. So when would we do that? It would be when we have, so it's gonna go up and down. So yeah, this is fine as well. Then we would have this, right? So it did hit the last uh column, so we would basically start rolling down, right? Up, down, up, down, up, and down. Oh, oh, right? 0 is going up, 1 is going down, 2 is going up, 3 is going up, 2 is going down, 4 is going up, 2, 3, 4, 5. Yep, that's fine. So for that case, we would do, our up is gonna be false. We would switch the flags, and we would definitely do what? Column plus plus, sorry, row plus plus. We're going downstairs, so yeah, that looks reasonable. Similarly, if we have our column is equal to 0, that is, we did hit this, where is it? That is, we did hit this piece, column is 0, we did hit this one here. If that's the case, we are going down, then we would go up. So our up is equal to true, up is equal to true, as well as we would do what? Row plus plus, right? We would not stay here, we would go to the next row and start going up. So row plus plus. Then if our, so that's hitting this left row. If we hit this one, like bottom, so that's basically r is equal to m minus 1. For that case, we would do, yeah, we would just flip that. Up is equal to true, and we would also uh increase the column number, like, yeah, so that's gonna be C plus plus. And at the end, I think on top, where should we do it? Let's say we have this piece, right? So we would just have a vector of integers, call it diagonal, and we would do diagonal dot push back. We would do that row, that column. This should suffice. at the end, return the diagonal. Let's try. No, what's happening? Seven bubble on the phone. What? Um, mm, I think I did handle all the cases up here. Let's just do that. Safe check. If is really equal to zero, and if it's really equal to and is less than n and c is greater than equal to 0 and c is less than n, and then that's a legit diagonal face. We try to push it down, see what we get. Wrong. We're not getting this piece, and so let's try this. Let's see where we're getting it wrong. We have this piece. We are struggling with this is the systems. Try to see if it's passing. And the answer is no. Was 2 5 4 0. What? Already started the last point. Reflection. That should be not really. Already using it as we start with down with 0. We're not using that. So started this. How many diagonals do we have? Mm, Start from this. Save. Each pass we enter 1 mm pass. So we do the size or Yep. Proper is tracking the data, like how many elements do we have? Hmm. So that arms is set up fine. This logic's working fine. Return is also good. This is kind of the bottleneck. So we have diagonals over here. Mm, then yep. See. Mm-hmm. Start to zero. Let's take this one. Yep. Okay. This one's decent. And the kind of problem was let's try to deal with it. So we had these starting from 0 to n times n plus 1 and d plus plus. That is basically n times n is 12 and 13. So we will have elements going from 0 through 12. Show why and how. So 1, 2, 3, 4. So 0, 0. So we have like 1, 2, 3, 4, 12 elements over here. We have to iterate from 0 through. Oh, yeah, that's right, that's right. 12 elements, right? So we have to iterate up to 13. 1000 plus 1. It's okay. So the typical array stuff. What's it?